Espinoza of our department, and he's going to speak to us about geomechanical challenges in CCS. So, Professor Espinoza, please go ahead.
Okay, thank you very much, Professor Mohanty. It's my pleasure to deliver this invited lecture today. And I'm going to talk basically about what are the geomechanical aspects or geomechanical concerns that we have to have, or we have to take into account when we design these geological carbon storage systems. Before we get started, let me encourage you to, at any time, just to interrupt me. This is not a seminar, it is a lecture. So just feel free to interrupt me or to write in the chat window. I'll try to keep an eye on that. And hopefully this will be smooth enough that we can interact throughout this entire lecture. Okay, so I understand that many of you are undergraduate students. Probably you haven't taken any class with me, or you don't know me very well. So my name is Nicolas Espinoza. I'm an associate professor here at UT Austin, and I've been here in the department since 2013. And I work on geomechanics applied to unconventional carbon geological storage, and most recently to geothermal energy. And today I'm going to talk about carbon geological storage. If you're not taking geomechanics right now, probably you have to take it in future semesters. So I teach PGE 334, which is undergraduate geomechanics. And also for the graduate students, if you're interested in more about this, I also teach advanced geomechanics that you might also be interested in. If you have any questions about this lecture, please send me an email, or also I encourage you to drop by my office, and also we can talk a little bit more about this. All right. So I think most of you are already familiar with carbon capture geological storage. So there is not much I have to say about this. Probably you have seen already this figure. But there's many things that we have to take into account as we design and we engineer these systems. First, it's very important the injection rate. What is going to be the injection rate that we use? You'll see that it's not the same as when we produce hydrocarbons. Second, what is the storage capacity? Similar as before, it's not as easy as calculating, for example, original oil in place or original gas in place. How do we monitor these systems? And how do we ensure that this is going to be safe in the long term? Also, if there are any issues with this, what is the liability for that, and how we can mitigate the risk of CO2 storage? And also very important, as in any engineering problem, is that we need to make sure this is going to be economic. Okay, so we're going to try to answer all of these questions, and we're going to answer it mostly from the geomechanics point of view. Probably you have seen already many of the challenges related to the reservoir engineering part. But before we get started, let's see a few cases. There have been already about 236 documented cases of CO2 storage in the world. And these are, quite a few, 236. But if we want to get to the level of storage that we need in order to meet the objectives, for example, of the Paris Agreement, we have to do more than this. So here are just a few examples. For example, you may have heard about the case in Sleipner, Norway. This was the first one which attempted storage only without EOR. And it has been quite successful. Probably one of the things that wasn't expected is that CO2 will rise so quickly through some thin shale layers. that weren't supposed to stop fully the CO2, but certainly rose quicker than people had thought. Most recently, there was, or there is, I should say, a very successful project in Canada called the Quest project. And here there are about 5 million tons of CO2 already injected since 2015. Something I like that you keep in mind are these injection rates, because this is something very important, also something that we need to take into account when we analyze the geomechanics of these systems. And most recently, in the Northern Lights projects, it is estimated that quite a bit of CO2 also is going to be stored in the North Sea. Okay, so how are we doing with CO2 storage? If you look at the current installed capacity, it's about 34 million tons per year. And the objective that we have for 2050 is about 4,000 to 6,000 million tons per year. So the question is, how do we get from where we are right now to the future, right? How do we meet these expectations? And that's not trivial, and geomechanics plays a role in this. So just to keep in mind some numbers that you might want to remember. In Texas, we produce about 340 million tons per year of carbon dioxide. And you can check these in this website of the Environmental Protection Agency. This is very nice. You can check state by state all the CO2 emissions, where they come from. And this is the case for Texas. And our objective would be that more or less in a couple of decades, we achieve 100 million tons per year. So that would be more or less the objective that we have for the future here in Texas. All right. So again, how do we go from here to there? And this is going to be the work that many of you probably are going to have to engage on. All right. So before we start with the details about geomechanics, let's just see a few basic concepts that are going to help illustrate the challenges here. If we think of a typical production rate decline curve as a function of time for the hydrocarbon production, which is the good case and which is the bad case? Can anyone tell me that? While I change the colors. Okay, no one is taking this one. This is an easy one.
The green one.
The green one. Okay, very well. Why? Because the integral of this is going to be the total production, right? But basically, look at something very important here. We want a very high initial production rate, and also we want a not very steep decline rate. That's very important. And for storage, it's going to be something very similar, because for storage, we want to achieve now the opposite, a very high injection rate that we can sustain in time. And we want to keep that rate more or less constant, or if it decreases, it doesn't decrease too much. So if you were to go to a place in which you start with a very small injection rate, but all of a sudden you cannot inject anymore, then the amount of injected CO2 is not going to be a lot. And also, if we add an environmental value or a money value to the amount of CO2 that we inject, this is not going to have a very high net present value because the initial injection is not high. So this is our objective, to have high injection rates and to keep those on time. But the problem here is that that presents sometimes some conflicts with geomechanics. And this is what we have to understand, how we put geomechanics into the design of these systems. When we analyze hydrocarbon production, sometimes you can pull from the wellbore or from the reservoir as much as you can, and there are not many problems with that. Probably you might have a little bit of some production if you pull too hard, if you lower the bottom hole pressure too much, but many times if the rock is competent, you can just pull as hard as you want and then just increase the production rate as much as you want to get sooner your investment, right? But for injection, we need to be more careful with this. And we need to optimize these injection rates so that we don't run into any problems. All right. Any questions so far? All right. If there are no questions, then remember, you can also write in the chat window. I'm keeping an eye on that. So when we put now mechanics into the picture, we see that some of the objectives of an ideal CO2 storage reservoir, as I was telling you before, are going to have some conflict with geomechanics. For example, we cannot assume that the entire pore volume is going to be equal to the storage volume because we really have to push, for example, brine to make a space for CO2. And as you may have seen already from the reservoir engineering point of view, this is not straightforward. But also that brine, if you push it out of the pore space, where is it going to go? And that depends on the connectivity of the reservoir. And that depends on how you can relieve the pressure out of the reservoir. And that's related to geomechanics, as we're going to see. Also, we need to provide reliable and safe trapping. And that's going to depend on the barriers that we have in our storage system. This could be a cap rock, or it could be a fault. And that's something that we have to understand too. Similar to what happens with oil and gas, if we inject CO2, we're going to have a buoyancy pressure that we need to make sure that it's not enough to go through some of these barriers, or it's not enough to reactivate some faults or fractures. And this is a little bit beyond to what we're going to see here, but not all rocks are the same. So there are some rocks that are safer than others. And again, this is a little bit outside the scope of our lecture today, but that's something that if you ask me later, we can talk a little bit about. Okay, so it's very important too that we have high and steady injection rates. And this is going to depend on many things. And we're going to go more into detail on this just in a bit. And it's also very important that we can monitor that. And also geomechanics plays a role on the monitoring of CO2 to ensure that it's safe in the subsurface. And as we're going to see, some of these processes, they not only include management of pore pressure, but also include geomechanics, changes of temperatures we're going to see, and also changes in the chemistry of the pore fluid, and also in the interaction between the rock and the CO2 and the brine. So that's something else that we have to take into account. All right, let's go into the specific of this problem. And these are the three main things that we're going to have to take care about when we consider geomechanics in carbon geological storage. First, we need to get to know what is going to be the injection rate. And we have to make sure that that's not going to fracture the injector or the cap rock, because that will defeat the purpose of keeping the CO2 in the subsurface. Then, what is the storage capacity? We need to make sure that as we inject these fluids, we do not reactivate any faults, or we do not produce a elevation of the surface that could affect some facilities, or could affect even some people that might be living on top. So we have to make sure that that's not going to be it's not going to cause any problems. And also we have to ensure that the injection of these fluids is going to be safe in the long term, and is going to, any chemomechanical alterations that the chemistry is going to be that is going to either play in our favor, or that is not going to have any high impacts on the rocks that we inject. Okay, so let's go one by one. First one is the injection rate. How do we limit, or what is that injection rate? In order to answer that, we need to go to a very quick class of Geomechanics 101. And you know, some of you probably are taking this class right now. Some of you will take it later, but let's just go very quickly through a review of stresses and the Mohr circle. Okay, you're all familiar with pore pressure, right? We know that in the subsurface, we're going to have a gradient of pore pressure. If we consider hydrostatic pore pressure, the higher the depth, the higher the pore pressure is going to be. And the gradient is how much the pore pressure changes with depth. Can anyone tell me what is the gradient of pore pressure with depth? How much pore pressure increases with depth in with hydrostatic with the hydrostatic gradient? Okay, let me see. I see a message in the chat. Very well. I see the answer already. It's about 0.44, 0.45, 0.46. It's about that PSI per foot. Okay. That's the pressure gradient of water or brine. Okay. But however, we have this other gradient, which is the gradient of total stress, or the overburden. And this is going to depend not on the density of water, but on the density of the rock, with the fluids and with everything. And this gradient, as you can see over here, is going to be, or is going to give you a stress which is higher than the pore pressure. And this gradient is about 1 PSI per foot. So it's about a little bit more than twice the gradient of pore pressure. So if, for example, you went 1,000 feet in depth and you try to literally lift the ground up, the force that you will need, or the pressure that you would need, will be equivalent to the stress SV, or the overburden. So at 1,000 feet of depth, you will need about 1,000 PSI per foot to literally lift the ground up. Okay, and as you see, it's higher than what you need to inject the fluid. If you need to inject the fluid in the subsurface, you need to go a little bit higher than this pressure gradient, so you can inject the fluid. All right, well, let's add 2 more lines in here. One thing is the vertical stress, but in mechanics, stress actually depends on the direction in which you measure it. And in addition to the pore pressure and the vertical stress, we're going to have somewhere over here what is called the minimum horizontal stress. And also we're going to have the maximum horizontal stress. What are the values of these? We really don't know. We have to measure those. There are some approximation of those, as we're going to see in just a bit. But if you really want to know those, you have to go to these places and do a hydraulic fracture test and measure those. That's the way of getting these numbers. And this also depends on where you are. Sometimes these horizontal stresses can be higher than the vertical stress. And that depends if you are close to a tectonically active region. For example, if you were close to some active mountain the word doesn't come to my mind, but a zone with active mountain building, then probably these horizontal stresses will be higher than the vertical stress. Maybe one of them, maybe both of them. That depends on the place in which you are. But in general, we don't know what these are, so we have to measure those. But the main message from this is that we have three stresses: the vertical stress and two horizontal stresses. So if we now make an abstraction of this and imagine a cube, which is the same cube that we have over here, then we're going to have a vertical stress, a horizontal stress, and a minimum horizontal stress. And the way we represent this in mechanics is through the Morse circle. So probably some of you remember the Morse circle from your materials class. And a Morse circle, we plotted with the normal stress on the x-axis and the shear stress on the y-axis, and it looks something like this. I'm just plotting here half of the Morse circle, where in this case, let me follow my color convention. Let's say that this is going to be the vertical stress. This is going to be my minimum principal stress. And let me actually make a small change here. I'm going to plot this as the effective stress. So if you have any question, please go ahead as I continue writing these parameters, and this is going to be half of my Morse circle. The Morse circle, the size of the Morse circle is very important because the bigger it is, the bigger the diameter, the more shear I have. The more to the right it is, the more compression I have. And if we want to take this into 3 dimensions, we can add the third stress, which is going to be in this case, the maximum horizontal stress. And that's going to give me 2 additional circles. And this completes the 3D Morse circle, where here, for example, sigma H max, this is an effective stress, is equal to the total stress minus the pore pressure. It's very important in geomechanics that we take this into account. The stresses, if we really want to know if they are going to fail our rocks or how much are going to deform our rocks, we need to subtract the pore pressure. And this is what gives me the effective stress, the difference between the total stress and the pore pressure. So here, sometimes you will see I use sigma with a tilde for the effective stress. Some other times I may use this other convention without the tilde, but both of these are effective stresses, and the same applies to the other stresses, vertical and minimum horizontal stress. All right, so now that we know what the stresses are, what the stresses are in the subsurface, we can, we're in a better position to see how we can limit this injector fracturing or fault reactivation. So let's go to that. First, how do we avoid hydraulic fracturing at the wellbore? Well, if this is the initial state of stress here in the reservoir, originally the rock is going to be in equilibrium. It's going to be happy over there, no problems. It's in equilibrium with the surrounding fluid. And that rock is going to be limited in the Mohr circle space by lines that bound the possible state. For example, this is the line for shear failure. This is the line for tensile failure. This is the line for which we will have a significant deformation due to compression. So our objective is to keep this Mohr circle inside this boundary. So it doesn't go into shear failure, it doesn't go into tensile failure, it doesn't go into enough, into too much compression. Actually, this is not going to happen too much in the case of injection, but it might happen with depletion. All right, so if some part of our rock goes into tensile failure, what we might have is a tensile failure at the injector. So our objective is to make sure that this doesn't happen, that we do not have any part of the rock going into tensile failure. The analysis is actually a little bit more complex than this, but let's just, for simplicity, say that this is what is going to happen with hydraulic fracturing. For fault reactivation, what we want to avoid is that any of these faults are not going to go into shear failure. In this case, a Mohr circle hits the shear failure line. And for the chemical alteration, we want to make sure that, for example, after a long time, if we inject a fluid, that the properties of the rock, which was the boundary that was now, that is with these lines, doesn't change so much, or the rock doesn't weaken so that even the initial conditions might go into shear failure. That's what we want to make sure is not going to happen. All right, so let's go with the first case of hydraulic fracturing. Let me see if I can get this video right away. I have the link over here. Just one sec. I want to make sure I have that window somewhere over here. Let me try to click. It's not getting there. Okay, this is not working. Just one sec. Let me try to copy this. All right, just one sec. It's just a technical problem. Let's try now. Okay. Yeah, now it is working. Okay, so let me bring this into the main screen. All right, so this is going to happen when we have a tensile failure. Let me pause it over there. This you may think this as the fracture. When fluid pressurizes a fracture, it's going to produce a tensile fracture that goes and extends from the tip. So this is what we're going to have, and try to imagine that, but in the context of the wellbore. That's what we want to avoid, and for sure we want to avoid that doesn't go through the cap rock. All right, so how do we avoid that? Actually, we have regulations about this, how to avoid the fracturing of the wells. For example, if you think about class 2 wells, there are some regulations that tell us what is the maximum wellhead pressure that we need to have for this to be safe. And most recently, there are regulations also about class 4 wells that are meant for geological sequestration. But let's keep with, let's talk about these equations, suggested equation, and what would that mean in terms of the fracturing pressure. So this would mean that, for example, if I have an additional 0.2 psi per foot to add to the injection pressure, that would mean that the bottom hole pressure would be the gradient of pressure that we said before, the pore pressure gradient, 0.44. We need something above 0.44 in order to inject any fluid. And what this equation is telling us is that the maximum that we can use is an additional 0.2 psi per foot. So the maximum injection pressure is 0.64 psi per foot. And this might work in some places, but it's not going to work in all places. This is just one equation, one suggestion, and there is no equation that is going to be safe everywhere. There is no one size fits all. So that's what we have to be careful about, not to use blindly some of these equations, because sometimes they may be wrong. So in order to design what is going to be the maximum injection pressure, we have to be a little bit more careful with this. So here let's see another example of this. How we incorporate this fracture pressure into design. So with equations that are based on linear elasticity, some of them you can look at them in my notes. This is a freely available resource that you can take a look at it at any time. You can demonstrate that the maximum injection pressure, the fracture pressure, is going to depend on the Poisson ratio of the rock, on the effective vertical stress. Here, this is the effective vertical stress, and the initial pore pressure. So that if this is your initial pore pressure, you're going to have a maximum pressure, which is going to be equivalent to the fracture gradient. So the objective is not to go above that pressure, because otherwise you may go into a fracturing of the wellbore. And here already we see one more extension of this, that it depends in which location you are also, that the initial pressure is not going to be hydrostatic. It happens in many offshore basins that the deeper you go, the higher the pore pressure is as you go deeper and deeper. And it's higher than the hydrostatic pressure. And that's sometimes a problem, because that also limits the range or the available pressure that you have for injection. So the pressure range for injection, as you can see over here, is going to be the maximum pressure or the fracture gradient minus the initial pressure. So this is a little bit better than what we saw before, but by no means is going to solve all our problems. In some cases, we might be much better off by doing what is called an injection test. And in that injection test, for example, you can do what is called a step rate injection test, in which you ramp up the injection rate of the fluid that you want to inject, and you measure pressure at the same time. Then you can make a plot of the injection pressure as a function of the injection rate. And if you plot this data, initially the initial points will line up in one line. And after you go to a certain pressure, this trend might break and go into another trend with higher injectivity. What that means is that at this point, you might have a fracture. That's why you don't have that much of an increase of pressure as before for an increasing rate. And the intersection of these two lines is what is going to give you what is called the fracture parting rate and the formation parting pressure and formation parting rate. So this is going to tell you what is the maximum rate that you can use for injection and what is the maximum pressure that you can use for injection. Any questions so far? Okay. Well, if not, let's continue. And now I'm going to show some cases. And the message is that either the regulation that we see over here, or the prediction of the fracture gradient with linear elasticity, or even these step injection rates sometimes might not be enough. Sometimes you need to be a little bit more careful in designing injection for CO2 storage. And let's see some examples. For example, this is an example in the North Sea. This is called the Snøhvit field case, in which about 1 million tons of CO2 were injected in 3 years. But a problem that they saw in this location is that just look at the stars. This is the actual data. The injection pressure and the bottom hole pressure increased a lot quicker than what they thought. And this is due to several reasons. One of them is that apparently this reservoir was too compartmentalized. What that means is that the faults which are bound in this reservoir didn't let the pressure relieve enough so that the CO2 was accumulating in this place and didn't have anywhere to go. So the pressure just increased up and up. Another suggestion for why this happened is that salt precipitated near the wellbore. This is like a case of salt scaling. Actually, CO2, if it doesn't have any water, is going to dry the reservoir and the rock around the injector. And imagine that if you have a residual water and that residual water has salt and you get the water out of the salt, then you're going to have precipitated brine, right? And if that blocks your pores, that could also reduce the injectivity of the wellbore. But what you have to make sure is that you don't go over the fracture pressure, which in this case is very clearly shown over here. And in this case, they didn't go over that. They measure pressure and they ensure that they didn't go over the fracture pressure. But you know, as we were saying before, sometimes this is a problem because probably your injection rate is not as high as you may have thought, and your storage capacity might not be as high as you thought initially. So this is certainly an issue that you have to keep in mind, and you have to design to avoid something like that. Any questions about this field case? Okay, well then let's go to the second one. This is a case in Mississippi.
Dr. Espinoza?
Yes.
I have a question. What is the depth of the first case?
The depth of this case, let's see if I remember correctly, it starts about 29 MPa. So the depth should be about 3 kilometers or so. This is offshore over here.
Oh yeah, thank you.
Let me see, I actually have the depth here in my notes. It is, the water depth is about 300 meters, and the total depth is about 2.5 kilometers. Okay. Yes. Okay, I thought I heard something. Let's go to the second case. This is a case here in the US, injection of CO2 adjacent to a CO2 EOR field. And in this case, CO2 was injected similar to a schedule to the one that we mentioned before with the step rate test, in which you ramp up the injection rate with time. And as we were saying before, sometimes in these cases, you might see that your pressure doesn't increase as much as you expected. And in some of these cases, that may be an indication of a hydraulic fracture in the injector. And something that we have to take into account too in these cases is the temperature of the injected fluid. Because a sharp decrease in temperature is going to de-stress the rock adjacent to the injector, and it's going to make hydraulic fracturing easier. So how do we make sure that this doesn't happen? What you do is you build what is called a mechanical model of the subsurface, and with your, for example, with your sonic logs and other logs, you can create and fit the variation of stress with depth and measure more accurately what is the variation of this minimum horizontal stress in the formation. With this is actually what is done in hydraulic fracturing, because with this you can not only predict if there is going to be a fracture or not more accurately than with the other models, but also you can tell if the fracture is going to stay in the reservoir zone or is going to go is going to propagate upwards or downwards. So this is something which is routinely done in hydraulic fracturing, and something which is also of a lot of benefit for now for subsurface fluid storage, because now we know a lot more about how to model these processes. But in this particular example, what I wanted to emphasize is the effect of temperature. So this is a study that we did with a graduate student and that was working with me, in which we model injection, and we consider this variation of the fracture gradient with depth, and also we consider the effects of temperature. And temperature is something very important because, as I was telling you before, there is something which is called a thermal stress. If you lower the temperature of a solid, it will tend to shrink. However, if you don't let that solid move, instead of developing a shrinkage, it's going to develop stress. And in this case, for example, if we were to increase the temperature of this solid, and we don't let the solid move to the top and the and bottom, is going to push these boundaries. If we were to lower the temperature and we had glued the ends of this rock to the bottom of the top, which is not moving, then we will develop a pooling at the ends. And the same can happen in the subsurface. And let me show a very nice example of this. This is an example of, let me see if I can pause this. No, apparently not. It's a GIF. So this is an example of injection of liquid nitrogen into a wellbore in acrylic. And what you can see are thermally induced fractures. So the solid tries to shrink in the proximity of the wellbore, but because it can't, because there is more acrylic next to it, instead develops these fractures due to thermal stresses. And something similar can happen also with our injectors in the subsurface. If we inject a fluid with a sharp decrease or a sharp contrast in temperature with the formation, what is going to happen is that the temperature around the injector is going to decrease, and that temperature around the injector is going to lower the fracture gradient. So that's something else that we have to take into account when we inject fluids in the subsurface, particularly if we are using very high rates. Because if we use a small rates, then the fluid is going to get into equilibrium very, very quickly with the surrounding formation, and it's not going to lower the temperature of the rock. But as we saw before, our objective is to increase or to inject as much as possible. And if that's the case, sometimes you might lower the temperature of the rock enough that it might lower the fracture gradient. And so that's something that you have to take into account, and something that is going to give you a different response of injection pressure if you consider these thermal stresses or if you do not consider them. Okay, any question about injector fracturing? We're going to move now to another topic. Okay, so if there are no questions, then let me move on. But remember that something we don't want to do is to fracture the injector, especially we don't want to fracture the caprock, which is
I got a question.
injector. Yes.
How much temperature decrease? Generally, I'm sure it varies from rock to rock.
Yes.
Can cause some kind of fracturing.
Well, it depends a lot on the type of rock,
right?
Because the stiffer the rock, the more stress is going to develop, and the softer the rock, the less stress, thermal stress, is going to develop. Actually, these thermal stresses, let me see if I have the question over here. Okay, these thermal stresses are going to be proportional to the thermal dilation coefficient and to the Young modulus of the rock. So in this sense, if we look more at the practical application of this, a relatively soft rock like a sand in a young sedimentary basin like the Gulf of Mexico or like the North Sea, as those are very good targets for injection, they will develop less thermal stress than a very deep rock, which is very stiff, like let's say like a deep carbonate or a very stiff shale or a granite. So this also depends. It's not only change of temperature, but also on the thermal dilation coefficient and the stiffness of the rock.
But a temperature change of, let's say, 30 degrees Celsius, will that generally cause some problem?
Well, you know, going into rough numbers, it's kind of difficult, but we really want to avoid very, very sharp changes, like more than a 50-degree C change, I would say, in general. But you know, that rule might change from place to place.
Yeah. And how fast, if this change occur, is that also an important factor? Meaning 50 degrees Celsius change over a year, maybe good, okay, but 50 degrees Celsius change in a day is definitely going to be bad.
Okay, well, the problem is also related to the injection rate, because eventually, if you inject slow enough, the fluid is going to draw heat from adjacent rocks, and the temperature is not going to increase that much. I would say mainly the problem would be when you have high injection rates and your temperature changes very quickly around the injector.
Yes, thanks.
Okay. All right, so let's go to the next case, which is fault reactivation. In fault reactivation, we have an initial state of stress that goes and bumps into the shear failure limit. And let me see if I can pull up the video for that. Why not? Okay, let me look at that. Try again. Okay, I'm gonna find this with a different method. Just one sec. So if you have any question, maybe you may want to think about that right now. As I pull this video. All right, so fault reactivation is going to be an example of shear failure. And shear failure is something that if you already took the geomechanics class, or if you're going to take it, is what happens when you load the rock in the triaxial loading, and sometimes also it would happen when you load it with in the unconfined compression test, which I'm trying to pull out right now. I think I'm very close. Just please bear with me and we'll see it. So, all right, here it is. All right, so here you have an example of loading of a rock in one direction with no stress on the sides. Let me find. The previous one failed at 3600. Okay, well, that's me talking. Let me mute myself. And at some point, when we go over the limit of stress, the vertical stress is too much, the rock is going to fail. And notice the angle of failure. This is a shear failure. And this is exactly what happens when, for example, we may reactivate a fault in this case. So that's what we don't want to do. We don't have to have shear failure in this case. And that's going to happen in cases in which, by decreasing the pore pressure, we move the state of stress and we move it towards the shear failure line. So we're going to increase the pressure in these reservoirs, but we don't want to increase it as much so that some of these faults might reach the shear failure limit. And we also have learned a lot about this recently from saltwater disposal. And we know that some of these faults, they do reactivate if we are not careful enough. Sometimes they might produce very minor earthquakes or a very small number of earthquakes. Like, for example, it happens with saltwater disposals in West Texas and also New Mexico. You see there is a lot of injection in some of these formations, not many earthquakes, large earthquakes being produced. But in some cases like Oklahoma with a different geology, we may have a large number of earthquakes induced by injection of saltwater disposal. Here you can see a very clear correlation of the injected amount of water and the number of earthquakes with magnitude larger than 3. So this is something that we also need to be careful about. When we inject a CO2, and as we move into large injection of CO2 volumes, we don't want something similar to what happened in Oklahoma to happen with CO2. We don't want to reactivate some of these faults. We don't want to produce any large earthquakes. And this has also been measured, for example, for CO2. This is a case in Illinois where in a CO2 injection project, there was also microseismic monitoring. And with that microseismic monitoring, it was possible to see that some of these faults, some of them that were not visible in the seismic maps, the seismic volumes, they appeared with the CO2 injection. That's because the CO2 was changing the pressure of the reservoir, changing the effective stresses, and getting some of those faults to reactivate in shear. Fortunately, in this case, most of the induced seismicity was very small, but that's something that we have to be careful about, and we need to include in our design of CO2 injection. All right, so let me start with an example over here about how we do this, how we compute those injection rates and those injection volumes so we do not reactivate faults. And this is a case, this is an example in the Gulf of Mexico that actually we work here at UT on trying to predict what is going to be the maximum injection volume and actually the optimum injection volume, combining injection rates and trying to simulate the injection schedule that will minimize the risk of fault reactivation. In many of these locations, offshore locations, we have faults, and we need to make sure that those do not reactivate. One, because of the issues I was telling you about induced seismicity, but also in some of these cases, some of these faults might also be sealing some parts of the reservoir. So if we break the seal, we might break the or defeat any purpose of storage. So we need to be very careful about this. All right, how do we solve this problem? And we come back to the Mohr circle here. What we have to do is we have to analyze what is the state of stress and how that state of stress is going to change when we inject a fluid, when we change the pore pressure. If we change the pore pressure and if we increase the pore pressure, the net result of this is going to be considering that the normal, in this case, the total stress is going to stay constant. If we increase the pore pressure due to injection, the net result is going to be a decrease in the effective normal stress. And what this is going to do is going to move this Mohr circle to the left because the effective normal stress is going to decrease. And depending on the orientation of the faults, we will get to know which faults might be more likely to reactivate in shear or not. For example, this is an assignment that we do in my advanced geomechanics class. We have a map of a faulted reservoir with several faults, and depending on their orientation, on the strike and dip of the faults, and the initial conditions of stress and pore pressure, we can calculate what is the available pressure so that those faults do not reactivate. So we don't want to go into shear failure. And many times we'll put a safety factor into that. So we make sure that the Mohr circle does not touch this line. In this example, all of these points over here, these are the faults, the actual faults. Faults in this case, 1 to 9. Actually solving this problem is more complex than the simple problem of the fracturing pressure, and but it is doable. So that's something else that we have to do and have to take into account when we predict how much CO2 can be injected. And a problem here, as if you remember what I was saying before, is compartmentalization, because it's some of these reservoirs or some of these blocks, like for example, let's pick this one. If this block probably is, it's a beautiful sand with a very high permeability, very clean sand, but if it is too much compartmentalized, if the faults adjacent to it are sealing the compartment, there is no much fluid I can inject because the brine cannot go anywhere. So that's going to, this increase of pressure is related to the level of compartmentalization, and is kind of the opposite of the aquifer drive. You remember that when you have a reservoir, the more aquifer drive that you have, the more oil you might recover because the aquifer drive, where in this case, we want to have an aquifer relief so that when we inject CO2, that brine that was originally there can be displaced. So this is going to be on the compartmentalization. And the available volume that is going to increase the pressure that much. So in this case, this is a simplified model, but you can go very complex on this. You can go to complex models like this one with faults that are 3D surfaces. Usually when you do this, you have to couple your reservoir simulation with a geomechanics module, something which is being, it is more and more popular in the petroleum industry to do this, to better understand these systems. Here in this example, in a work that we did with the graduate student, also we measure, let me show some videos here. What we're going to do is we're going to inject CO2 in this sand, and we're going to analyze what is the change of stress in this fault. And as you might expect, if we inject the fluid, pressure is going to increase very quickly. The pressure front advances much more quickly than the fluid injection front. And as a result of this injection, and after we stop injecting, in this case, let me see, stop injection. Now, the pressure is relieved, and then the CO2 goes up. And I don't know, you can see very clearly here, but these are the shear strains, in this case, the plastic strains developed by fault reactivation. We want to make sure that this fault reactivation doesn't compromise the fault sealing capacity if there is a fault which is limiting the movement of buoyant fluids. All right, so I see that we're getting close to the end here. I have 10 more minutes. So let me go quickly through a few more slides. Something very important too is what is the compressibility of the reservoir. Same as with oil and gas reservoirs. If you remember, there's something which is called compaction drive. The softer is the rock, the more is going to get squeezed as you deplete the reservoir, and the more is going to be able to push fluids out of it. Well, for injection is the opposite. And what you want is a high compressibility so that the porosity can deform and can take an increase of pressure with a large deformation. So if I have a very stiff rock, I'm not going to be able to inject that much because the pressure is going to rise very quickly because the rock cannot deform. So we want something that can deform and that can accommodate the increase of pressure. So in this case, again, coming back to the Mohr circles, and we are in a process of injection, what we want to measure is what is the compressibility of the rock, but not under depletion, but under injection, which is something a little bit different than the usual value that we have in oil and gas for depletion. And that's something that is, it can be measured. It's not actually easy to measure, but it can be measured and it's very important because the lower the compressibility of the rock which is being injected, again, the higher is going to be the increase of pressure for a given amount of injected CO2. And here I have one example, which is going to illustrate this concept. In this case, what we did was simulate injection with permeable faults with different types of compressibility. And if you were to use the compressibility, which is usually used for depletion, you will predict in this particular case an injection of an increase of the pressure in the reservoir of about 1 megapascal or 140 psi. But if you use the right compressibility, the increase of pressure is actually twice as much. And this is very important because, again, we run into the problem of predicting what is going to be the storage capacity. If you design a system with assuming that the pressure is not going to increase as much, and if you go to the field and then you see that your pressure increases much quicker than what you thought, then that's going to be something that probably you don't want to do. And very important too is to quantify what is the pressure relief at faults. The more permeable faults are, the smaller the increase of pressure is going to be at the reservoir because you can push that brine out of the reservoir. However, with a high level of compartmentalization, the smaller the permeability of the fault, the higher the pressure is going to rise and the quicker it's going to rise too as you start injecting carbon dioxide. So this part is a little bit more complex than the previous one, but you can solve it. And again, you can do this by coupling reservoir engineering and geomechanics. Like in this case, we also added a computation of a net present value to take into account the credit that we get for injecting CO2 and perform several numerical simulations and use a machine learning model to optimize the location of an injector to also optimize the schedule that will give us a higher net present value. So that's something that can be done and should be done in these cases to optimize the injection of CO2, keeping in mind that we do not engage or we do not go into any geomechanical risks of, again, fracturing the injector or causing full reactivation. Okay, so I think, let me see, what time is it?
You have another 5 minutes.
Okay, I have another 5 minutes. So I like to go to some questions. So let me go very quickly through this last part. As I was saying before, something that we want to do is also to monitor some of these places. If we inject a fluid and increase the pressure in a formation, we can cause what is called a surface heave. This is something that actually also happens in oil and gas, but it's kind of the opposite, right? if we produce a fluid and we decrease the pressure, the reservoir is going to be compacted. And that compaction is going to lead to a depression of the surface, something which is called subsidence. And in some places, like in this case in Long Beach, California, there have been like severe cases of subsidence. In this case, 26 feet of subsidence. This is quite a bit. And for CO2 storage, it's going to happen the opposite. When we inject a fluid, the rock is going to expand and the surface is going to go up. For example, in this case, in Algeria, with CO2 injection, it was measured a surface elevation of more or less 15 millimeters. That's not much, particularly thinking that this was in the middle of the desert. So there are no people, no facilities, no nothing that was really compromised. But that's something that you also have to take into account in cases in which the surface heat might compromise surface facilities or people living on top of that. All right, so for the chemomechanical part, I will make this very short. CO2 mixes with water, that creates carbonic acid, and that alters the rock. Sometimes rocks might weaken, sometimes rocks might get stronger. In fact, sometimes that geochemical alteration can cause precipitation of minerals along conduits of fluid flow that could potentially seal some fractures. So it's not really straightforward to analyze this, but we know that this happens, and we know that we have to take this into account. There are some formations which are more prone to chemical alteration, particularly those that have carbonate minerals, and there are some other formations and other types of rocks, like sands or shales, or I should say clays more than shales, that react very little with CO2. So we know that those are going to have a very small chemomechanical alteration, but that's something that we certainly have to keep in mind. And we have done some studies related to this, measuring the changes of properties. This is a case, this is a field trip that we did to Utah and examine a fault and measure what are the changes of the geomechanical properties exposed to millions of years of a CO2 leak. And in cases, sometimes it changes very little, as in this case, and sometimes it changes a lot. Sometimes the strength even increases. That's an example for the shale I don't have here. But that's something that we can study, and then we should study. In the laboratory, we can tell what are the rocks that are going to be most reactive to CO2, and that's something that we certainly have to keep in mind. All right, so I'm running out of time, so let me skip through this and go to the conclusions. When we inject CO2, we're adding energy to a system, and that energy somehow is going to release. Our objective is that that energy does not get released geomechanically through failure of the rock. And we have to take into account geomechanics into the design of these carbonate storage systems, a lot more than the typical workflows for oil and gas production. And the things that we have to be careful about are mainly injector fracturing, fault reactivation, and also seal integrity. And these are going to depend on changes of pressure, changes of temperature, and also sometimes are going to depend on geochemical interactions of the CO2 with the resident brine and with the rock. So again, I'm going to open now the floor for questions. If you want to stay around, I can stay around a few more minutes, but remember, most of my material can be accessed online at these web addresses and also through YouTube. So you can find all of that in my YouTube lectures.